Alright, hi everybody. So today I want to go over another fundamental counting technique, and it's called complementary counting. Alright, so let's learn about this, because if you saw my casework video, you would know that there are a few fundamental counting techniques in math. Casework is one of them, and so is complementary counting. Alright, you can't get good at counting if you don't know complementary counting. So let's get right into it. So by definition, complementary counting is a counting technique where we count what we do not want. And this is often much easier than counting what we actually do want to count. So over here, as you can see, I've given you two visual aids just to show you what complementary counting is really all about. And this is just how I like to think about it, because it really brings the point home. So you can either think of complementary counting as this little rectangle over here, or you can also think of it as this circle over here. Now, it doesn't matter which diagram you choose, but just try to stick to one and understand what the diagram is trying to say. So in both diagrams, we have two parts, what we want and what we don't want. And we can see that the part that we don't want is a lot smaller than what we do want. But notice how what we want and what we don't want, they both make up a whole. What we want and what we don't want make up this whole over here. And this is your big clue to use complementary counting. Basically, if you find that your casework is getting a little bit messy, that would be your first cue to use complementary counting. But also, another big hint is if you can just do some thinking at the beginning, and before you do too much work, you can just sort of see, okay, what I want to count seems a little too big. A little too big or a little too intimidating, but the complement, so that would be what we don't want by definition, and that's why it's called complementary counting. But if you notice that this complement is a little bit easier to work with, or it's a little smaller, a lot of times it will be easier because it is smaller, then that is your big clue to use complementary counting. You can see this portion over here, what we don't want, is much smaller than what we want. So those are just some of the things you want to look out for before you dive into a problem using complementary counting. But once you do decide that you want to use complementary counting, we need to get familiar with the concept of something that I've called, just in quotes, the opposite. Because this is very fundamental to complementary counting. So for complementary counting questions, a lot of times what you're going to do is you're going to take the question given in front of you. So in this case, our first example is how many 3-digit integers are not multiples of 7? And what you're going to do is you're going to take this question and you're going to ask yourself the opposite. So if I were to do that for this question, it would look something like this. Instead of asking how many 3-digit integers are not multiples of 7, we're going to ask ourselves how many are multiples of 7. I'm going to make that eraser a bit bigger. Now we're going to move this over because this is our new question that we're going to ask ourselves. So you can see we've turned this original question and asked ourselves this new question. We can do the same thing over here. We can ask ourselves, how many 4-digit integers are perfect cubes? Let's say we're given that as a question. Well, if we want to change it to its opposite, what we're going to do is ask ourselves how many 4-digit integers are, and then we're going to stick this word not perfect cubes. So sorry if the writing's going up a little, but the point is we have transformed a question by asking ourselves the opposite. And to really drive the point home, we can see the opposite of this phrase, are not, is the word are. And similarly, it goes the other way too. The opposite of are is are not. So over here, I've given you a little handy chart for some of the most common phrases that a question can be worded. So on the left side, I have when a problem asks ... how many are not, I want you to think instead how many are. As we saw just above, that's how we change the original question from this to this. If you are asked how many are, I want you to ask how many are not. And the opposite of how many have at least one, well, it would be a phrase that goes something like how many have none. And again, I cannot stress this enough. You would only ask yourself the questions on the right side if the ones on the left seem difficult. So if this one seems a lot easier to answer than this one, then that is your cue to use complementary counting. So now that I've given a brief introduction to what complementary counting is, the idea of the opposite, and some of the most common ways a question can be phrased, let's go over a little workflow. So this is going to be our main method. It's going to be a 4-step process, and this is how we're going to approach every complementary counting problem. The first thing we're going to do is ask ourselves the opposite. And I put opposite in quotes because that's not really the correct, precise term in math. In math, what we call the opposite, so I'm just going to go back up here. This is really, if you're really interested, this is actually something called the negation. But that's a topic for another day. For now, we're just going to think of it informally as just the opposite. So changing things to its complete opposite. Okay? So that's what we're going to do first. You're going to ask yourself the opposite question. So that's why we went over it before. Your second step is to count the total possibilities with no conditions. So the reason why we do this first, we focus on the total possibilities first, is because what you're going to find, at least what I found when I approached complementary counting, is I would count what I didn't want, but then I would forget to subtract from my total possibilities. And you're going to see this in action, so don't worry if this sounds confusing, but basically a lot of times we forget this very important step, and then we end up counting the wrong thing, so we get the wrong answer. Step 3 is where we count what we don't want, so that's the complement. And then step 4, going back to what I said earlier, we have to subtract what we don't want from the whole in order to get what we want. So I can summarize that as steps 2 minus step 3. So going back to what I said before, a lot of times I would just leave the number I got for step 3 as my final answer, but remember, that's what we do not want. So we need to subtract from the total possibilities to get what we do want, which is why step number 2 is also just as important. But a lot of times I would forget step number 2. So I don't want you to forget that, so you're going to take care of the total possibilities first. Just get that out of the way, and then you should get the correct answer because you won't forget it. Alright, that was the vague theory. Let's get into some practice problems to see how it really works with our first question. So question number 1 says the Caruana family has 4 sons and 3 daughters. In how many ways can they be seated in a row of 7 chairs such that at least 2 boys are next to each other? And first thing we see right away that stands out is the phrase at least. And if you go back to our chart, you might know how I'm going to change this question up. And yes, we are using complementary counting. So, what makes this a perfect candidate for complementary counting? Well, aside from the fact that I said so, it's also because there are some big clues that tell us complementary counting is the way to go. For example, if we tried to approach this with casework, so counting directly by breaking this problem up into cases, you're going to find that it could be a little overwhelming because there are so many possible cases. For example, let's just write a valid seating arrangement. We could first have 4 boys and then followed by 3 girls. But that's not the only way. So this would be one case. But guess what? There are some more valid seating arrangements, such as maybe 2 boys, followed by 2 girls, followed by 2 more boys, and then 1 final girl at the end. We could also have a boy first, followed this time by maybe 2 girls, and then we got 2 boys. Maybe we could stick a girl here and then a boy here at the end. So already we have 3 completely valid seating arrangements, but that's also 3 cases. And keep in mind, these are not the only 3 cases. So we can see it can get pretty messy pretty fast, and it's going to be hard to tell if we actually counted every single case. So we can see casework leads to too many cases. However, there is only one way to assign the seats so that no 2 boys are next to each other. That's right, there is a single way, and let's see if you can find out what that way is while I write that very important point down. So there's only one way to seat the children so that no 2 boys are next to each other. And in case you have not figured it out yet, it would be something like this. Boy, girl, boy, girl. Boy, girl, and finally boy. So that's just boy, girl alternating, and I know I'm saying boy and girl even though it's son and daughter, but oh well. I guess we'll use the letters B and G instead of S and D, okay? So basically what we have done is we have now taken this original question and changed it. So now we're going to ask ourselves, in how many ways can the children be seated in a row of 7 chairs such that no 2 boys are next to each other? Go back to the chart. Remember, the complement of at least is none. So now instead of at least 2 boys, now we have no 2 boys. And that's the question we're going to answer. Now before I do that, I am actually already breaking my own rule, which is kind of funny and sad. So anyways, let's answer our first question actually that we should tackle is how many possibilities are there with no conditions. So basically if there was no condition of, two boys have to sit next to each other, then how many seating arrangements are there? We can answer that very quickly. 4 sons, 3 daughters, so there are 7 chairs, which means without any restrictions, there are 7 factorial ways to assign the seats. So let's emphasize that there are no restrictions. Yeah, see? Good thing I caught that. I was actually about to break my own rule. Anyways, do as I say, not as I do. Now we can go back to counting the complement, which would be this. This is the complement because it is the complete opposite of what we are trying to count. So now our new question would be something like this. How many ways can this seating arrangement occur? So BG, 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 B. So this time, a seating arrangement like this, where it goes boy, girl, alternating, we have 4 factorial ways to seat the boys, and then we have 3 factorial ways to seat the girls. So there are 4 factorial times 3 factorial ways overall to seat the children. Let's just say them. So that no 2 boys are next to each other. Let's just copy that. Okay? Cool. So, everything would seem great. You would probably take this answer over here, you would write it down, you would highlight it, you would box it, do whatever, and say that's your final answer, and then you would be wrong. Because remember, this is what we do not want to count. So the thing about complementary counting is a lot of times students will mess up at the very last step because either they get too excited or they just forget that we need to use all our numbers and we need to do some subtraction because we counted what we don't want. This means overall there are actually 7 factorial, so that's the total number of ways without any restrictions, and then take away this number, 4 factorial times 3 factorial. You can get out a calculator and do that yourself, but what you're going to find is the final answer ends up being 4,896 ways. Don't like that 6, so let's fix that. There we go. That's our final answer, and that was complementary counting in action. I hope you see that was not too bad. We just had to think about the specific form of a seating arrangement which we don't want, and then we subtracted that from the total number of ways. So again, I want to emphasize the point. Complementary counting simplifies everything because there's only one way so that no 2 boys are next to each other. 1 is much less than 3. And it's not even 3, it's actually more cases. So casework is not the way to go for this. Complementary counting is the way to go. Now let's see if I hopefully don't make this mistake where I forget to count the number of ways without any restrictions in the next problem. which goes how many 3-digit integers are not multiples of 5. So again, just by intuition, before we even do anything, we can tell that this is a very good candidate for complementary counting because we can sort of just see in our head there are a lot less multiples of 5 than there are not multiples of 5. And forget about 3-digit integers. Just look at the first 5 positive integers. So that's 1, 2, 3, 4, 5. You can see only one of them is actually a multiple of 5 and 4 of them are not. So we can see there are a lot less multiples of 5, and a lot less means it's a good candidate for complementary counting. So we would change the question. I'm not going to rewrite the whole question out again, but we would change it by doing the following. We would ask ourselves, how many 3-digit integers are multiples of 5? So we're going to get rid of that not. And that's the question we're going to answer. How many 3-digit integers are multiples of 5? But before we do that, remember, we cannot make the same mistake as before. So we need to ask ourselves, how many 3-digit integers are there in total without any restrictions? So this just goes back to the multiplication principle. I won't go over this in too much depth. You should already know this, but basically we have 9 choices for the first digit, 10 choices for the second, and 10 choices for the third, which means overall we have 900 3-digit integers. So now let's count how many of them are multiples of 5. So the way we're going to do that is we're going to start off by asking ourselves, what's the smallest 3-digit integer which is a multiple of 5? And then we're going to ask ourselves, what's the largest 3-digit integer which is a multiple of 5? And then everything else in between will be counted. So then we just need to find out how many numbers there are. So let's start off. So the smallest 3-digit integer is actually 100, which already is a multiple of 5, which is great. 100 is a multiple of 5 because it's the same as 5 times 20. 105 is the next 3-digit integer which is a multiple of 5, and that can be rewritten as 5 times 21. So this is great. This keeps going until, when do we stop? Let's see, 1000 is a 4-digit integer. Not interested in that. But the multiple of 5 just before that is 995, which is the same as 5 times 199 when you break that down. So we have 100 and 995. And you can imagine everything in between. So somewhere along here we'll have the number 455, we'll have 725. So all multiples of 5 are included in between 100 and 995. So now we just need to count how many there are. Now the easiest way to do that is to ignore this factor of 5 that we have over here and just rewrite this as a list of numbers based on the other factor. So as I said before, just completely ignoring the 5s, and then that leaves us with a list that goes something like this. We are left with the number 20, 21, and this goes on to 198 and 199. So that's how we're going to count this. So if you do not know how to count how many numbers there are from 20 to 199, where we go up by 1, there is this neat little trick where you just convert this into a easier list. And you're going to do that by subtracting the same number from every term. And we're going to subtract 19. So 20 minus 19 is 1. 21 minus 19 is 2. 198 minus 19 is 179. 199 minus 19 is 180. And this should hopefully be easy to see that there are 180 numbers from 1 to 180. This means there are 180. So I hope you like that neat little trick I showed you over here, by the way. This is pretty common in math. Just taking a list of numbers and subtracting the same number from each term, because you're not changing the number of terms in the list when you do this operation. Anyways, there are 180 three-digit integers which are a multiple of 5. But of course, I think you're way ahead of me. This is not what we want to count. We don't want to find out how many three-digit integers are a multiple of 5. We want to find out how many three-digit integers are not multiple of 5s. How would we find that? Well, we would take our number at the start, 900, and subtract the complement to get what we want. So that's 720. Three-digit integers which are not a multiple of 5. Let's just take that. Cool. Sorry if the writing's getting a bit messy. I am kind of rushing this. Okay, let's go to the final problem of the day. Yes, there are only 3 questions because there's not much to complementary counting. So we have 3 questions in class and you have 3 homework questions after. But for now, let's stay focused and answer this final question. So our final question of the day tells us to find how many numbers between 100 and 300, keyword being inclusive, that means we include 100 and 300, but how many of them are not perfect squares? So, again, before we even do any work, I think we can all agree that there are less perfect squares between 100 and 300 than there are not perfect squares. And you can just very quickly go over them in your head. So there's 100, 121, 144. You see that gap is getting pretty big. So all other numbers are not perfect squares. And there's a lot more of them. So the fact that there are a lot less perfect squares makes this the perfect candidate for complementary counting. And we're going to change the question by asking instead, how many numbers between 100 and 300 inclusive are perfect squares? So first, we are going to deal with how many numbers there are without any restrictions. So just how many numbers between 100 and 300 inclusive are there? And again, going back to the list idea from before, if we want to find out how many numbers there are between 100 and 300 inclusive, what we're going to do is we are going to convert this list by performing an operation, and we are going to subtract 99. This way, 100 becomes 1, 101 becomes 2, 299 becomes 200, and 300 becomes 201. So there are actually 201 numbers between 100 and 300. So, not 200. It is not 300 minus 100. It is 300 minus 100 plus 1. So that's 201. So we know that's something to keep in the back of our mind. There are 201 numbers between 100 and 300. Cool. And now we're going to ask ourselves instead, how many of these numbers are perfect squares? So that's the question we're going to ask. How many of these numbers are perfect squares? And the way we're going to do this is just by writing them out. So we're going to go through them one by one. So the number 100 itself is actually a perfect square, so that's great. And it's the same as 10 squared. The number 121 is 11 squared. As I said before, the next number is 144. That's actually 12 squared. And this will keep going. There's not too many of them because we're only going up to 300. But the number 289 is 17 squared. And the number 324 is the next perfect square. It's 18 squared. 18 squared. Too big, so because 324 is greater than 300. So the numbers we're interested in are 100, 121, 144, all the way up to 289. And again, the way we're going to count this is by converting these perfect squares to another list that goes 10, 11, 12, all the way to 17. And from here, I'm not going to go over the list trick again, but there are 8 numbers. So you can do that yourself if you want. So you can take all of these numbers and subtract 9. And always remember, this 8 is not your final answer. You need to combine these two numbers, the one you got at the start without any restrictions and the complement, because we are interested in how many are not perfect squares. Therefore, there are 201, take away 8 is 193. So there are 193 such numbers that satisfy the conditions given in the problem. Alright, I'd say that was a pretty productive session. That is complementary counting. I'm going to highlight this, by the way, because I forgot to do that. Anyways, that was complementary counting. I hope you see that that was not too terrible. We just ask ourselves, if it's easier to count what we don't want and subtract from the total, then that's the way to go instead of counting directly. Question number 1 especially showed that if casework gets messy, so in other words, if you have too many cases, it's time to take a step back and think of complementary counting as a possible method of attack. Great. Now that the in-class questions are done, you have homework. So we have 3 questions. So all of these questions can be solved with complementary counting. So I'm not going to answer them right now. Obviously, that will be in the solution document, but we can go over them very briefly. Question number 1 asks, how many 4-letter words with at least one vowel can be constructed from the first 5 letters of the alphabet? So using complementary counting, we would instead ask ourselves how many 4-letter words with not at least one, but no vowels. So how many 4-letter words with no vowels can be constructed from the letters A, B, C, D, and E? And of course, you subtract from the total number of 4-letter words with no restrictions. Similarly, for question number 2, how many 5-digit numbers have at least 1 2? You're going to ask yourself, how many 5-digit numbers have no 2s? And question number 3 asks, in how many ways can 8 people be seated in a row of chairs if 2 of the people, Emma and Chase, refuse to sit next to each other? So I've given a valid seating arrangement over here and a invalid seating arrangement over here, because over here they're sitting next to each other. That's not allowed. Over here they're far apart, which is good. And the way you would change this question is you would keep everything the same. So in how many ways can 8 people be seated in a row of 2 chairs if 2 of the people, Emma and Chase, instead of refuse to sit next to each other, maybe we can instead say if they insist on, sitting next to each other. So now we have to keep them together like this, as a block. And that's my hint to you, as a block. So basically, instead of splitting them apart, we're going to keep them together. And then, of course, you will subtract from the total number of ways 8 people can be seated in a row of chairs with no restrictions. And then we will get the final answer. And we will find out how many ways this toxic couple can be seated under these conditions. Okay? So there we go. That is complementary counting in a nutshell. So pay attention to the visual aids and the negation, as well as this handy dandy flowchart I've given you and a workflow. So these 4 questions over here. And you should be able to answer any complementary counting question. So with all of that out of the way, we now have another very important counting technique, which is great because we're just going to keep building and building. It's going to get very exciting. So now we have casework and complementary counting. Well, guess what? We're going to be adding more. So I hope you're excited for what's to come, and I hope you enjoyed this video. I will see you in the next one. Bye. Happy solving!